Welcome back. We're now going to be looking at Chapter 19. In Chapters 17 and 18, we were looking at or investigating the concepts of electricity and building the foundation for how we can use electricity to transport energy around. And in Chapters 19 and 20, we're going to be looking at how we can use these moving charges, using the energy that they carry, to take energy from where we have it, power plants, hydroelectric dams, those kind of things, to where we need it, your house, your phone, everything else. So we're going to be looking at chapters 19 and 20. We're going to combine the two of them together, and we're going to be looking at how we can use that. And we're going to start off with Chapter 19 by talking about current and resistance. And, oops, hang on one second. Get rid of that. Oh, it's one of those things. Hang on. There we go. All right, so we're going to talk about current. And we've kind of already mentioned this before when we were talking about our difference of potential, and if we have a positive object here, and if we have a negative object here. And I said, hey, what happens if we put a conductor in between the two? And we stated that charges, I used the word electrons before, would flow from the negative to the positive until they equalized each other out, okay, until both sides had the same net charge. Well, we define this movement of charges as current. And basically, it's going to have the symbol I. I is going to be for our current, and it's going to be equal to the number of charges that pass by in any given time. Now, you're going to hear me say this analogy a lot. I like to give you the idea of moving electric charges is kind of like being like a river. And the charges going through are kind of like the water that's flowing through. So you can kind of think of each charge as being like an individual water molecule. And as it flows down through the river, that's kind of what we're talking about. So if you have a large current, those charges, those water molecules, that river is going really, really fast. If you have a relatively slow current, it's going to be going slow. So I'm going to continually refer back to the idea of a river going through. But here we have our current. This is our I, which travels through. And this is how we defined it in the last chapter. When we looked at that difference of potential, we talked about voltaic cells and the magic electron mover. Now, there's a glitch here. Remember a few chapters ago, I talked to you about how Ben Franklin assumed that it was the positive charges that moved. Remember, he had that concept of ether, and that it was when glass rods got rubbed by the silk, they would gain ether. And in essence, the glass rods were gaining positive charge. With the rubber rod and silk, the rubber rod would lose that ether, so it was losing those positive charges, becoming negative. Everything we do was based off of that idea that positive charges move. We now know that's wrong. Ben screwed up. But because of all the conventions that were in place, Faraday using a positive test charge, the positive plate being the higher potential, we still use that today. So we will state, so if you have, and I'm going to do this, if you have something, if this is a positively charged object, and this right here is a negatively charged object, and we put two conductors there. So here you have a conductor right here. Our regular one states that the electrons, and this is what happens in reality, the electrons are going to flow from the negative to the positive. And this is what's called electron flow. Due to conventions of what Franklin said, though, here is my conductor coming back. Those were positives going this direction. This is what's known as conventional current, because that's our convention. The positive charges are the ones that are moving. Okay, again, we know that this bottom one is wrong. In reality, it's backwards. But if you think about it, the end result is the same. Because if we look at the bottom one, conventional current, as positive charges go from left to right, this side becomes, I'm going to put this all in black. This is going to be easier. This is less positive. And this is more positive. when the charges move. Up here, we look at the electron flow as the electrons go over. This up here is going to be more negative. This is going to be less negative. Well, less negative and more positive, they mean the same thing. More negative, less positive, they mean the same thing. And so the end result is the same. It really didn't matter how we got there. It's still going to end up with the same result. And so we're going to continue to use conventional current, even though it's backwards from reality, because everything is based off of it. We will state that positive charges move through our conductor. And you can argue with me about this tomorrow and say that it's dumb, because every year we have this conversation. But just know that regardless of how you feel about it, the end result's the same. And so just because we pick one way or another, it really doesn't matter in this case. Okay, so let's do the conventions. All right, so I just want to just explain the positive charges make up the current. It's called conventional current, the opposite of electric current. And again, like we said, it's backwards to real life, but that's okay, because the end result is the same and it's all right. Okay? Now, there are sources of current, and I want to talk about this really, really briefly. Batteries and generators, and this is huge, and I am going to highlight this. They provide the energy needed to move the charges. A lot of people think that batteries or generators provide the charges so that they can move. The charges are already there. The charges are in the conductor. The charges are already on our plates. It's just that batteries and generators provide them the energy to move, the impetus to actually go from that high potential to the low potential down. Okay? Now, other things I want to point out, batteries will convert chemical energy into electrical. We've talked about that. That was the last thing in the last chapter. Generators, which we'll talk about in chapter 22, convert mechanical energy into electrical. But regardless, the law of conservation of energy is obeyed. So again, key thing, they provide the energy, not the charges. The charges are already there. Okay? The charges are already in there. It's just that batteries and generators provide the energy to get them to move. Now, there are two types of currents that we are going to look at. Okay? In this chapter, actually, in this chapter, we're going to focus on one of them. But there are two types of currents that we use in the world. And the first is called direct current. And if I were to graph this out, excuse me, if I were to graph this out with current versus time, this graph would look like this. It's constant. It doesn't matter. The current is going to stay going constantly in one direction. It flows from the positive to the negative and is going to continue to go at that amount the entire time. That's why it's called direct current, because it goes in one direction. So it goes in one direction whole time. Whereas the alternating current, and I'll put that here, alternating current, and I got I and T, I'll put this in orange. Alternating current constantly changes direction. Okay, so constantly changes direction. Now, both accomplish the same thing. They both provide energy to our circuits. Both provide energy to go from one spot to another. How they do it is slightly different in each case, but they both accomplish the same thing. We will primarily deal with direct current because A, it's easier to understand, and it's safer. And when we do our labs in here, we will be dealing with direct current. Direct current is what comes from a battery. Okay, it all flows in one direction. So if you've ever licked a 9-volt battery, what you felt going through your tongue, the tingle, was direct current. Alternating current, that's what comes out of your wall. And that's what the vast majority of our electronics run on, is alternating current. Okay, and it fluctuates back and forth, back and forth. And if we are still in school, you will have an opportunity later on in chapter 22 to feel what alternating current feels like going through your body. It's not dangerous. You don't have to worry about it, but you'll get an opportunity to feel that. So we'll discuss the benefits of both later on, but just know that for our purposes, we're going to live in the world of direct current just because it's easier. Okay, so we're going to end there, and we'll pick up again tomorrow. So we'll try some sample problems, have some fun with it, and discuss tomorrow. So everybody have a great day. We'll see you later. Bye.